fan of power pop. Who isn't? If you're not a fan of power pop, get out now. Okay, good. You're still here. I'm welcome to Bite of Physics, number 83. I'm John Mallinckrodt, your host. I'm a retired professor of physics who loves infecting small numbers of people with a love for physics. So that's what we do here. Let's see. So what are we doing today? We're doing the third episode of my Newtonian mechanics series. And we'll see kind of how far this goes. I don't know. This could stretch on forever and ever. We're going to finish up what I'm calling the static equilibrium subset of the Newtonian mechanics. We're going to move on into Galilean invariance and then into impulse and momentum and work and energy and a bunch of things like that. But we're going to intersperse these episodes too with fun things. I was thinking just the other day, I came across people were talking about gyro compasses, and they are a fascinating thing, which I actually didn't know much about until recently. So we may intersperse with a gyro compass thing if I can figure out a way to present it simply. It's a really kind of complicated topic, and it does have to do with torques, as we've been talking about as well. Anyway, well, I will leave that there for right now. We'll get started in a second. Say hi to Shamash. Oh, good. Sam's here too. Shamash, good to see you. How are we doing? Are we streaming today?
Yes, we are. I caught you early today. We're loud and clear on YouTube. Link is already in chat. Hello to you. Hello to Sam and Benjamin. Everyone else. Hi.
Good. All right. And let's go to Sam first, and then we'll go to Benjamin.
Hi,
hey,
guys.
Sam. Good to see you.
Good seeing you. Hope
How are you
everybody's
doing?
well.
How are you feeling?
I'm recovering.
Yeah. Well, that's good
Yeah,
to hear. It
thanks.
sounded a little scary.
Yeah, it was really scary. I had never been in that situation, but I'm glad everything went well.
Yeah. No, you sound good. So
Yeah.
that's really good to hear.
I didn't know. Sorry that you were that sick. I thought you were just away with family or something. I'm sorry to hear
No,
that. I'm
I
happy
had
you feel okay now.
I had a serious atrial fibrillation arrhythmia episode. And so what made it dangerous is that my blood pressure fell to 80/70,
Whoa.
which is kind of door's death. I mean, death's door. And so yeah, so it took them a while in the ER, but everything is sorted out.
All right. Very
Yeah.
good. And Benjamin, welcome to the stage as well. How are you doing this morning?
Good morning. Good morning. I'm so excited today.
What's that? Why is that?
I just know that today is going to be the day that I get
Here
an
we go.
explanation for why people believe in quantum entanglement.
Yeah, it fits right in
I'm looking
with
forward to it.
the static equilibrium topic, I would say. So yeah, maybe we'll get to that too.
Very excited.
Okay. Well, maybe I'll toss you a bone somewhere. Who knows? Okay. Well, let's go ahead and get started. As I say, this is the third episode, final one. We're going to do examples today of static equilibrium. I've got a couple of kind of fun things I think for you along the way, but we're going to also learn about friction and springs. Those are a couple things that are kind of worth just getting under our belt, how they work along the way. So let's just launch right into it. First example is the classic. This is the one that drives people screaming away from introductory physics classes with boredom probably as much as anything. But it's a highly instructive example, a block on an inclined plane. And we're not even going to make it as interesting as it usually is because this is going to be a block that's just sitting there. This is not a block sliding down an inclined plane. This is just a block sitting there. And so we can analyze it pretty quickly. I've already kind of taught you how to start problems like this. You identify a system to apply the static equilibrium condition to. In this case, I guess you could choose the wedge, the plane itself, but it's not quite clear what it's in contact with, except maybe more earth or something. So the kind of obvious system to apply the static equilibrium condition to is the block. And I've drawn the required dotted line around it so that we can follow that dotted line. Notice there's only one thing touching it. And I've taught you that that means that there are exactly two forces acting on it. A force from the thing that's touching it, and this mysterious force that acts without the need to touch, gravity, the thing that gives the block weight for some reason. So you have two forces. One is down, and therefore the other one must be up because they have to add up to zero. Not only must it be up, but it has to be the same magnitude as the downward force. The only way you can add two vectors to get zero is if one of them is exactly the opposite of the other, as is shown in the vector addition there at the far right. So we conclude that the force that the inclined plane exerts on the block is 10 pounds upward. And that doesn't seem very interesting. Is that really all we can say? If that's all we could say, then this seems like kind of a silly example. So but we know there's something to be said because there's a question about something like how steep can that incline be and have that block actually be in static equilibrium? Because obviously, in general, you put a block on an inclined plane, it won't be in static equilibrium. So we need, and we know kind of intuitively that has something to do with friction. So we need to understand a little bit more about friction. And that's what I'll do in the next frame. Then we'll pause for a moment and see if there's any comments on this. So what we do whenever we have surfaces in contact is we tend to break that single force. There's just a force that the surface is exerting on the block, but we break it up into a component that's perpendicular to the surface and a component that's parallel to the surface. The one that's parallel to the surface, we all kind of understand intuitively as what we call a frictional force. Friction forces always act kind of along surfaces, where the normal force is just the force that that the plane exerts on the block. It's the Newton's third law counterpart of a force that the block is exerting on the incline. And together they form what you might just call the force of contact between the two. If I press that block into the incline, then that force will get greater. I can make that force be greater by taking my hand and pushing the block into the incline. And your intuition ought to tell you that if you do that, there'll be more kind of potential friction as well, that the frictional force is tied to that contact force. The more the two are pressed into contact with each other, the more friction, the more ability for that thing to stay there you might expect to see. So we just say all of that. I haven't gone into anything more than just breaking it up here. But you see that those two forces that I'm now showing in red have to vector add to give me the original 10 pounds up. That F we already determined, capital F, is 10 pounds up. So those two red forces have to add up vectorially, the way we're kind of learning just by context to do, tip to tail or tail to tip. I draw the normal force, and then I draw the frictional force, and I put the tail of the frictional force next to the tip of the normal force, and then the result is from where I started with the normal force, its tail, all the way to the tip of the frictional force. That's what those two forces are equivalent to. And I emphasize here, lots of times students hear this word normal force, and they get the idea that every time you have a statics problem, you have to put in a normal force because it's normal. It's just something that's always there because it's normal. But that's not what normal means. Normal is an archaic word for or a mathematical word if you want, for meaning perpendicular. So when we talk about the normal force, we're talking about that perpendicular component. And it's not something that's just always there because it's regular or usual or anything else. Let me stop there just for a second, see if anybody has anything to say.
So it always bothered me as a student whenever we're thinking about these problems, because my brain is messed up, I think, that somehow the plane or the surface of the incline is making this precise calculation, knowing that, oh, I can provide this amount of friction, so I'm pushing up on the block with that amount. And it always bothered me on a philosophical level that, of course, the mathematics runs beautifully. I just feel bothered by that fact that the incline seems to know what it's doing or something like that.
Yeah, no, that's the point you're making is a really good one, and we're going to talk about that some more here, because we're talking about what's called static friction, and static friction is particularly weird. I can put a block on an inclined plane, and then I can raise it to higher and higher and higher angles, and as I do that, if the block is going to continue to stick, there's going to have to be more and more friction, pretty obviously, on an intuitive basis, to keep that block from slipping. But there comes a point where it can't stay anymore. And so as we'll see on the next slide, sorry, not on the next slide, as we'll see soon, that frictional force has a kind of a maximum value that it can call on. But if it calls on that maximum value in all situations, it'll be too much. And the thing you could imagine that if that maximum friction were happening in general, it would actually make the block move up the plane, and that doesn't make any sense. Friction is complicated because it's fundamentally, you have to look at it microscopically as if there were little, if you look at the rough surfaces, there'll be little points of contact if you want. And those points of contact end up creating little compressions, just like the blocks we talked about last time. I should have drawn a diagram of this. Those little points of compression will get bent downward. And the more they get bent downward, the more force they apply up. It's a kind of an analogy to the compression idea, until they simply can't bend enough, or they can't, or the points of contact simply kind of shear off, if you want to think of it that way. Thinking about friction on a theoretical basis is complicated, and that's why we're not going to do that. We're going to come up with a heuristic model using coefficients of friction, as they're called, which works pretty well, describes frictional surfaces pretty well, not perfectly. Lots of situations that you can make up where it doesn't, but I'm getting ahead of myself. Anyway, enough to say that that's a good point, and we'll get to it soon. So let's look, if we reanalyze this now on slide 4 with this normal and frictional force thing. Now we have 3 forces. So now there's a little more interesting stuff to say. Those 3 forces have to add up to 0. I'm showing them down there at the bottom, adding up to 0. If you start with the normal force, you just place it somewhere. And then from its tip, you draw the frictional force. And then from its tip, you draw the weight force, and you have to get back to 0. So you could draw those in different ways, but unless you make sure that you draw them in such a way that you end up forming a triangle out of them, coming back to 0, coming back to the starting place, you haven't drawn them in a properly scaled manner. And it is that triangle ultimately that helps me do the trigonometry or whatever that I need to do to analyze it. And that's what we're going to do here. So first of all, do you see why the incline angle theta, which I think I didn't say, but is specified on slide 2 as being 30 degrees. So that angle theta there, the Greek letter theta, is 30 degrees. Do you see why that angle is the same as the angle that I'm showing in the triangle? That's not obvious. It becomes really obvious if you do these problems for long enough, and I have a way of thinking about it myself. But can anybody want to explain why that angle theta in the force triangle is the same as the force theta on the actual inclined plane itself? And while I'm asking that, I'll just say hi to Hero, Andy, and Ben. Hero
Hello.
/ Andy and Ben.
Sorry,
Hey, Sam.
I really don't understand the question. If you could, so the angle theta, I see the angle theta, but you're saying that is equivalent to what?
So I specified that the angle of the incline, that
Right.
theta in the incline, is 30 degrees. And then you'll see that I've shown that same angle in the force triangle. But it's clearly not, it's not in the same orientation at all. Where do I get the gall to claim that that angle in the force triangle is the same as the angle of the incline? This is a minor stumbling block that introductory students often have, so we need to kind of get by that.
Is it any more than just, well, we're dealing with a bunch of parallel lines, so the angle in between them is going to be the same? Like, do you want a more sophisticated?
Well, I think
explanation?
I think you're thinking the right thing, but it is definitely more than parallel lines, right? I mean, I see no lines in the triangle that are parallel to the lines that angle in the wedge or between. In the wedge, I see a downward slope and a horizontal line. And in the triangle, I see a kind of a steep upward slope and a vertical line. Right? So why are those two angles the same? Go ahead, Andy.
Well, I'm sure there's some geometry phrase like, opposite interior angles or something like that. But the way I always think about these is I always imagine that angle at 0 and imagine it sweeping to 90. And I just sort of convince myself that as this one was, if theta is 0, then the other theta is 0, and as it moves to 90, that they're going to be the same the whole time. Totally just seat of the pants thinking, but that's how I think about it.
That's exactly how I think about it as well. So I did want to one time go through the rigorous reason, but then really urge people to do exactly what you just said, Andy, that what you do is you just imagine what would happen to those angles if the angle of the incline changed, keeping in mind the perpendicularity. Ben, I saw your welcome, and I saw you unmute too. Did you want to say something more than that?
Not really more than that. I was just going to say Z angles, but not really more than that.
Yeah. So I put a couple of dotted, if you look carefully at the diagram of the incline, you see I put a couple of dotted lines in there as well. So if I take that vertical line and the horizontal line right at the vertex there, that's clearly a right triangle. And then I have drawn another dotted line that makes a right triangle with the incline itself, right? That's perpendicular to the incline, just like the vertical is perpendicular to the base of the incline. So if there's a 90-degree angle between the vertical and the horizontal, and there's a 90-degree angle between the two inclined lines there, the plane and the perpendicular to the plane. And those two perpendiculars share that angle between the incline and the vertical, which turns out to be a 60-degree angle. If theta is 30 degrees, then clearly that angle between the base, between the horizontal and vertical, between the vertical and the incline is clearly 60 degrees. But that same 60 degrees is part of the right triangle, or the right angle that is formed between the incline and the perpendicular to the incline. And so the remainder over there which you see is the same as the angle in the triangle, has to be 30 degrees, has to be the angle theta. That's such a complicated way of thinking about it that I really do. I'm sorry even to have spent so much time, but it's always something. It's worth pointing out that whenever you have a situation like this involving just a series of parallel lines and perpendicular lines, that triangle there, clearly one of those angles is theta. There's a there's a right angle in the force diagram, and one of those angles has to be theta. So you just figure out which one it is by kind of imagining wiggling that angle theta in the physical diagram and seeing what it does to the force diagram. Maybe that was more than anybody should have ever said, but hopefully that's helpful. And it is exactly what you said, Andy. That's exactly what I do as well. And I think it's what everybody comes to pretty quickly. Okay, enough said about that. So either way, yeah, go ahead.
Even more simply, I would just say how many degrees have I tilted the slope of vertical, and therefore how many degrees is the normal force of vertical.
That's right. Yeah, that's right.
So the reason you gave, John, and you think is complicated, is still easier than the one we learned in school. And the one we learned involves proving the two triangles similar. So you have to do a lot more.
That's right.
It's still simpler than the one you proposed.
No, that's right. And proving the triangles similar is the thing I just start off with, right, in the method. It's what Andy was saying. It's not, that's the part you just gloss over. You know they're similar. So the only question is which one is the angle theta? That's really the only question you're trying to ask. You're trying to answer. So either way we do that, we can now use the fact that that's a 30, 60, 90 right triangle and immediately write down that the frictional force is 5 pounds because the short leg in a 30, 60, 90 right triangle is half the hypotenuse, which we know is 10 pounds. So the frictional force is 5 pounds, and then you can use Pythagorean theorem if you want. 10 squared minus 5 squared square root is 8.66, or you can just remember that the long leg in a 30, 60, 90 right triangle is the short leg times the square root of 3. Either way you do it, you get that the magnitude of the normal force is 8.66 pounds. More generally, however, it's nice to be able to work these problems when you don't have, when it doesn't, it's not just a simple 30, 60, 90 right triangle. And that's where trigonometry comes in. And I'm not gonna go through trigonometry except to say that trigonometry allows you to find the side opposite one of the non-right angles by multiplying the hypotenuse by the sine of that angle. And it allows you to find the leg adjacent to that angle by multiplying the hypotenuse times the cosine of the angle. And that's all I've done there at the bottom, is to multiply, is to do that. 10 pounds. Sine of 30 degrees is a half, so you get 5. And
So,
cosine of 30 degrees is square root of 3 over 2. So you get 8.66. Go ahead.
Yeah, just very quickly, if you accept that 30, 60, 90 gives you 5 pounds, then you can use Pythagoras. You don't even need trigonometry here.
Right, yeah. No, I said that, I think, too. 100 minus 25, square root of that, square root of 75 is 8.66. Okay, so let's now address the problem we still haven't talked about. So here's what we know now, is that frictional force is 5 pounds and blah, 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 and it's static and blah, blah, blah. But we still haven't really, there's something nagging at us.
Hold on. Can I stop you? So let's say this box is on a frictionless surface at that angle. And for me to make the block stop sliding, I will have to exert a 5-pound force parallel to the surface.
That's right. Yeah,
if
that's
I
right.
exert more than that, the box will move up. If it's less than that, it'll move down. To be exact, it's static. It has to be a 5-pound force.
That's right. And the only minor correction I would make, because, and I don't really want to get into it deeply yet, is that we have to be careful whenever we talk about moving to ask whether we're talking about moving as in velocity or moving as in the word we don't mention around here yet, accelerating. In other words, is it moving, just moving? Because moving is one
it's gotta
thing,
be
or is it
accelerating,
accelerating?
right? It's
Yeah,
accelerating.
I knew you
that's
were going to be that pedantic, John. I could just,
Yeah.
as the moment he said it, I'm like, John's going to cover this A word. He's going to drop the A bomb.
Hey, cut me some slack. I'm a chemist. Yeah,
and it's handy though.
accelerating. Yeah.
It's handy though because we're going to talk specifically about that. I mean, that's going to be an important thing in our final exam question today. So it's a good precursor for that. But that's right. You could, of course, even if even if the plane were frictionless, you could just exert a 5-pound force up the plane, and that would also keep the block in static equilibrium. So that's right. Okay. So, but there is this nagging question. I mean, there is the possibility that it won't be in static equilibrium. Maybe the block, there simply can't be that much friction, in which case it's going to slide down the plane. So to deal with that, we have to talk about kind of the hard problem. It is, as Shamash said, kind of philosophically troublesome in a way that this thing that we call the static frictional force, and we'll deal with kinetic frictional forces as well in a bit, that a static frictional force can be whatever it needs to be up to some maximum amount. And it is kind of akin to a block sitting on top of another block with the block underneath supplying whatever force it needs to supply until that force is so great that the bottom block gets crushed or something, along those lines. It's very similar to that if you think about the way friction works microscopically. Ben, I saw you getting very angry there for a moment.
It's all okay. You just swore with the P word, but it's fine.
All right. Okay, so let's see.
It sounds like the F word phonetically, but it's spelled the P word.
Okay, so to be able to talk about that, we notice that frictional forces do depend on how hard the surfaces are pressed together, right? I mean, I could increase the possible stiction of that incline if I made the block heavier, right? For one thing, I could apply more frictional force, or I could just press it into the surface without trying to push it up the incline or down the incline. And that would also increase the frictional force. So it depends. The frictional force depends on the surface, and it depends on how hard the two surfaces are being pressed together. So we just come up with kind of the simplest model of friction. And this is a classic example of a model. It's not based on any theoretical underpinnings, although you can make a theoretical argument for why it makes sense. And it does work pretty well. Simply to say that there is a maximum friction, and that should have been a small f there. I'm going to label frictional forces with small f, so I just changed that. If you refresh, you'll get the right thing. The maximum frictional force is given by F max equals some coefficient of friction, static coefficient of friction, as we'll see in a minute, times the normal force, the force with which the two surfaces are pressed together. That static coefficient of friction characterizes the nature of the two contacting surfaces. So on slide 6, you'll see a table. I just stole this table from somebody off the internet. And it's a table of kind of typical values for both static coefficients of friction and kinetic coefficients of friction, which we will use in a little bit as well. Just looking at the static coefficients of friction in the first column there, you'll see, for instance, steel on steel, 0.74, et cetera. One thing you'll notice is that they're all less than 1. They don't have to be. One of them actually is 1. And they can be greater than 1. It's just that they usually aren't. To get coefficients of friction greater than 1, surfaces that can actually sustain larger sideways or along the surface force than into the surface force, are difficult to achieve. Dragsters have to actually make their coefficients of friction with the ground be as much as 4 or more. It's really the limiting factor for a dragster is trying to get those tires to stick to the ground well enough that they can get that the ground can exert a frictional force against the dragster, equal and opposite to the dragster frictional force against the ground, large enough to make them accelerate at the rate they do. And that does require static coefficient, or I shouldn't say static, it requires coefficients of friction of 4 or more. So you try to make tires that essentially glue themselves to the concrete, and you hope it's not concrete, you hope it's asphalt with lots of little ridges and things that the tires can grab, because you really want those tires to be able to push on the ground. And I saw you, Ben, you have a comment on that?
Well, just a figure I remember, and it is easy to calculate, that is about 0 to 60 in about 2.4 seconds is the limit for a coefficient of friction of 1. So any car that can do it faster than that, like a Tesla Model S on plaid mode or whatever, then you're talking a coefficient of over 1, actively sticky tires.
That's right. And dragsters these days do 100 miles per hour, get to 100 miles per hour in 1 second. So that's the kind of friction that you need. Friction you need to get to accelerate to 100 miles per hour in 1 second is truly fantastic.
Well, that's assuming you don't eject gas. I don't mean as in break wind. I mean
rockets.
Yeah,
Right.
because Musk was talking about on the future roadster. It'll probably never come to this, but he was talking about actually giving up your back seats for a compressed air tank, and then being able to have like RCS, reaction control thruster type things, to do cold gas ejection, not only to help with accelerating but braking and cornering.
Okay, we're gonna stay away from that acceleration word, though. It's really hard to. I guess I'm gonna have to cut us all some slack on that one from time to time.
Going faster quickly.
Sorry?
Going faster quickly. How's that?
Going faster quickly. Yeah, more quickly.
You're almost allergic to the A word as I am to the philosophy word. Oh, sorry, I said it. I swore. The F word.
Okay. And in that table too, the next column has the kinetic coefficient of friction, which is a little simpler thing to understand. When two surfaces are sliding, then the coefficient of friction gets a little bit easier to deal with, because there's no decisions to be made about how much force to apply. When surfaces slide, pretty much the frictional force is just some constant, the kinetic coefficient of friction times the normal force. You don't have this same kind of philosophically problematic maximum force that you're comparing your required frictional force against. Anyway, we'll get back to that too. But you'll notice that the kinetic coefficients of friction are always less than static coefficients of friction. If that weren't the case, you can think about that down the line, what that would mean. Not necessarily greater, but never more than the static coefficient of friction. That would cause a weird thing to happen if that were the case. And we won't talk about that unless we want to in the discussion. So let's go back now with that in mind, and just suppose that in this case, the static coefficient of friction is 0.7. That's pretty big coefficient of friction. So these would be pretty rough surfaces, or maybe glass on glass. When you have surfaces that are very smooth, you can have fairly high static coefficients of friction too. But at any rate, we're going to have a relatively high static coefficient of friction. And now we can just ask and answer the question, can this block be in static equilibrium? And we do it very simply. We simply calculate the maximum possible friction force by multiplying that static coefficient of friction times the normal force, which we have calculated to be 8.33 pounds, and we get that the maximum frictional force would be 5.83 pounds. And since the required frictional force is 5 pounds, the block will stick. So really the end of this problem, if I had stated all of these parameters from the beginning, would be just really the question: can this block stick to this incline? And the answer we've come to is yes, it can, because the required frictional force, 5 pounds, is less than the maximum frictional force that you could get given the angle and the weights and all those kinds of things. All right, so that's all I have to say about that example. Oh, and it's not quite all I have to say about that example. One of the things I want to stress in the things we do today, or at least in a couple of things we do today, is that it's nice to work out equations without numbers sometimes, because then you can answer other questions than the one that was asked in the first case. And we can do that here. We could ask, what is the minimum coefficient of friction that will allow the block to stick in this case? This one's pretty simple. The minimum coefficient of friction would be that which makes the maximum available force equal the force that's required. If the maximum possible frictional force was 5 pounds, then it would stick, but that would be the minimum coefficient of friction that we would require. So if I just take F max equal 5 pounds and stick it in the definition of the static coefficient of friction, essentially, I get that the minimum coefficient of friction is 0.6. So I could have a coefficient of friction as small as 0.6, and it would still stick.
John, another quick reference point, if that's okay. Just easy one to remember. So that coefficient of friction of 1 lets you accelerate 0 to 60 in 4 seconds. But it also lets a car sit on a slope that is exactly 45 degrees, because a triangle that's 1, 1, root 2, you have one unit of, you can just imagine a 1, 1, root 2 triangle. That's 45 degrees. That is a coefficient of friction of 1 as well. So the other way of testing the coefficient of friction would be to put, say, I'm using a car in this example, a block on a slope, and tilt the slope up until the block slides or the car slides. So a car stuck on a road with its brakes jammed on will probably start slipping when the road inclines to about 45 degrees if it has a coefficient of friction between the tires and the road of 1.
Yeah, that's right. And you can see that by looking at the back at the force diagram for instance, on page 7, and imagine that angle theta was 45 degrees. If the angle was 45 degrees, then the frictional force and the normal force would be the sides of an isosceles right triangle, and therefore they would be the same, right? They would both be in this case 10 divided by the square root of 2 pounds, and that would make the coefficient of friction F over n, F max over n, be 1 for just as you say.
That's your 1, 1, root 2 triangle, yeah.
Okay, other comment. Oh, so let me just finish slide 8, and then we'll finish this example. We'll go on to a second one. So I could ask this: with the coefficient of friction of 0.7, what is the maximum incline angle on which the block won't slide? Clearly, I could raise the incline to a larger angle if I wanted, since the coefficient of friction of 0.7 gives me some headroom, gives me more maximum frictional force than I need. So in that case, what I'm really asking is, at what angle would the required frictional force F equal the maximum frictional force F? And here I have to be careful, because the whole now I'm changing the force diagram. So I simply use the fact that the frictional force is equal to the weight times the sine of theta, as we determined before. Now that theta that we're putting in is the maximum possible theta for which it won't slip. and I set that equal to mu s times the normal force, which is the weight times the cosine of theta, if you look back to where we actually worked out what those were. So the nice thing is that when I do that, I put in what the frictional force is, I put in what the maximum frictional force is, I set them equal. I have the weight on both sides, so it cancels out. It doesn't matter what the weight of the block is. The only thing that matters is the ratio of the sine of the angle to the cosine of the angle. And that's a thing, if you know your trigonometry, that we call the tangent of the angle, the ratio of the sine to the cosine. So that happens, the maximum incline happens when the tangent of that maximum angle is equal to the static coefficient of friction. And so to make contact with what Ben was just saying, it turns out the tangent of 45 degrees is 1. That makes the coefficient of friction, that would make the coefficient of friction 1. But in this case, we know the coefficient of friction is 0.7. So if we want to know what the maximum angle is, we have to solve for the angle whose tangent is 0.7. And that's what we mean when we say arctangent. The arctangent of 0.7 is the angle whose tangent is 0.7. And you can use your calculator, you can look that up, and you get 35 degrees. And that makes sense, right? It's a little bit steeper than 30 degrees. That makes sense, just like the fact that the minimum coefficient of friction was a little less than 0.7. So both of those answers, you always want to make sure your answers make sense. And so we've done that. Okay, so that's, you can see why this problem makes, sends people running and screaming from physics. I don't know if that happened to you, Sam, for boredom or philosophical confusion, but I know we make a lot of chemists that way. Probably biologists too. Okay.
I've shared in the chat, John, just so we're not taking for granted that people can actually go to a calculator and do an arctan. Not everyone can still do that after their traumatic experiences at school. So I've annotated a diagram in the chat of how to do that specifically on your iPhone. It's just 3 or 4 button presses.
Oh,
so
good.
You can take any of those coefficient of friction values and then just do an arctan. If it doesn't work, make sure that you're not in radians mode. Make sure that rad isn't on the screen.
Right. Okay, let's, I want to do, I was going to do another kind of serious torque example, and I just decided that I would just talk about this one example, which I think is kind of fun, the idea of stacking blocks and getting an overhang. It's a fun thing to do with dominoes, right? Try to stack dominoes, get as much overhang as you can. And it at least gives you the idea of where torques are coming in. So if I just imagine I have identical blocks. I'm going to have a bunch of identical blocks. They're all uniform. They're rectangular. The center of gravity, if you want, is right at the center. They're not spongy. They're all of these things. But they do compress, of course. They have to compress a little. And I just put one of those blocks on top of the other as long as it is centered, as long as it's placed with its center above the surface of contact. We just know intuitively that that's going to work, right? The problem comes when I try to extend the top block too far. But this is what's happening torque-wise. When I do cantilever a block out, there is some torque due to the part of the block that's cantilevered that does want to tip that block in a clockwise direction. It isn't able to. It's not enough to do that, but it relieves some of the weight from the far left end of that block. So you get kind of a distribution of upward forces on that upward block from the lower block that I won't guarantee looks like I've shown there, but looks something like that. And if you calculate the net result of those upward red forces and that downward weight force on the block, on the top block, first of all, the sum of all those red forces has to add up to the downward weight force. That's just the force balance. And then the torque balance equation basically says that the clockwise torque from all those smaller forces to the left has to balance the counterclockwise force from the red forces to the right, around around a point just below the center of that block, if you want to think of it that way. Lots of ways of calculating the torques, but if I calculate them around the point just below the center of the top block, you can kind of think of it that way. Just the torques due to the red forces, since the weight force provides no torque about a point right below it. It's not going clockwise or counterclockwise. Maybe that was too much to say. But as I move that block further and further away, that distribution gets more and more unbalanced until when the center of mass, center of weight, center of gravity of the top block is right above the edge of the lower block. Now, the only way that thing isn't going to tip is if the total upward force, which is required to balance the weight, is acting along exactly the same line as the weight force. If those two forces don't act along the same line, then the normal force necessarily would be to the right, because it can't exist to the left of that. Would necessarily be to the left, because there's nothing to provide any upward force to the right. So at this point, that force is all right there. And you can imagine, I think we know intuitively, that top one is going to start to kind of tip, right? It's not going to be contacting the lower block in any serious way, except right at that point. So if I want to get maximum overhang, that's what I do. And clearly that means I've pushed the top block out by 1/2 its length over toward the right. So that's the maximum overhang I can get there. Well, let's imagine stacking more and more blocks, but I'm not going to stack something on top. If I put anything on top of that and try to extend it further, it's just going to topple things. I can't do that. But I can take this whole system now, this system of 2 blocks, and I can put it on top of a third block. And that's what I do on slide 10. Let's take the system of those first 2 blocks and put them on top of a third block, and then move it over and over and over until once again, the normal force on the system of 2 blocks is being applied totally right at that force, at that rightmost point of contact. If that's the case, then I can simply calculate torques about that point of contact, and the only way I'm going to get them to balance is if the weight force from the middle block is the same distance from that point as the weight force from the top block. They have to both be a quarter of the length of any block to one side or the other. And that's what I'm indicating there. So you have one force trying to make it rotate clockwise, the one on the right, and you have another force trying to make it rotate counterclockwise, the one on the left. And those two torques can only be equal if the two distances from that pivot point are equal. So now I've got an additional overhang of 1/4 L. The total overhang of the top block now is 3/4 the length of any block, 3/4 its length. So now I've got 3 blocks with a pretty good overhang, more overhang. Now the question is, can I add a third block? But once again, I'm not going to add it on top. I have to add it on the bottom. I take this system of 3 blocks and on slide 11, put it on top of a 4th block. Now I have the system of 3 blocks. Things are getting a little complicated now. I'm going to once again look at torques around the one point of contact there at the right edge of the lower block. But now geometrically, it's just mathematically, geometrically, it's getting a little complicated. And all I've really done is told you the result. Working this out would require you to do a little algebra. I didn't want to go through that. I just wanted to show you the result and show you why it's true. It turns out that you can now extend the system of 3 blocks by a distance of 1/6 the length of a block, an additional overhang of 1/6. And if you work out what that means that the weight force from the top block is now 5/12 of the length over 5/12 of the distance from the pivot point, the red vector pivot point. That's 1/4 plus 1/6. 1/4 is 3/12. 1/6 is 2/12. If I add those up, I get 5/12 L. And that means that the second block's weight is now 1/12 of the way, 1/12 to the left of the pivot point, and the top block, you have to work this out, turns out to be 1/3 of the length, or 4/12 of the length. And you can quickly kind of calculate, as I've done there, to see that the torques, the net torques, if I extend that overhang another 1/6 L, the net torque will be 0 again. So that is what you get. And you can continue doing this. It gets more and more complicated, and you really want to do this algebraically. And then you want to make the proof that I'm about to claim the result of using mathematical induction is really the way to do it. Shamash can teach you that, I think, when the time comes. But I'm just going to give you the result because it's fun. You see a pattern developing: 1/2 L, 1/4 L, 1/6 L. If you were to, guess at the next overhang, you might guess correctly that the next overhang is 1/8 L. That is correct. And the next one is 1/10, and the next one is 1/12, and 1/14, etc. So what you end up with is this series: 1/2 L plus 1/4 L plus 1/6 L plus 1/8 L plus etc., etc. For n blocks, you would have n minus 1 terms, right? With 2 blocks, you get the first term. With 3 blocks, you get the first and second terms, etc. So if you had 10 blocks, you'd have 9 terms in that series. And I can write that series by factoring out a 1/2 L from each term in there, and I get 1/2 L times 1 plus a half plus a third plus a quarter plus a fifth plus a sixth, etc., etc. And that series is called, anybody? Oh, well, I guess it says it right there. That series is called the harmonic series, and it's what's called a divergent series, because if I add those numbers long enough, I will get a number bigger than any number you want. It won't surprise you that that series gets bigger than 2, probably. It might surprise you that it gets bigger than 10. If I add up, I can get an overhang that would actually be an overhang of 9. I can get an overhang of 9 times the length of a single block by doing this. So it might surprise you that it gets to 10. It would almost surely surprise you if I told you you could have an overhang 1,000,000 times the length of a block. But in theory, you could. This series does eventually get to 1,000,000, and so on. And I've shown you some of the things. It takes only 4 terms to get to 2. It takes 11 terms to get to 3, 31 to get to 4, 83 to get to 5, and so on. 1,674 terms. You'd have to have 1,675 blocks to get an overhang of 8, and you'd have to place them perfectly, and you'd have to make sure that there was not a breath of air, and all sorts of things. So this is really a mathematical curiosity in the end. But as I say there, you'll find out that each time you increase the overhang by 1, you increase the number of blocks by a factor that approaches a very famous number called Euler's number, E, the so-called base of the natural logarithms. And you can use that fact to calculate that you would need something like 4 times 10 to the 43rd blocks to get an overhang of 100 times the length. And you'd need 10 to the 87th blocks, more than the number of atoms in the known universe, to achieve an overhang of 200 blocks. So I guess in theory, even in theory, you're probably not going to, well, in theory you can, but some practical problems there. Sorry, I kind of ran through that. You may have resonated with it. I didn't want to get too lost in the math, but this is just a fun example because technically, theoretically, you can make that overhang be as much as you want due to the magic of the harmonic series. And I'll shut up for a moment. Somebody wants to scold me for wasting that much time or say another fun thing about that. I'm all ears.
I'm just surprised that you need only 4 terms to get over L factorial.
4 terms to get over L fact. What do you mean?
I'm just being the scum of the earth mathematician that I am.
Oh,
You said surpass 2, and then between parentheses bigger than L, and then question mark. I just had to do it. Sorry.
okay. I'm not sure I followed that, but okay. Well, at any rate, so I did want to just talk about that. It's a nice application of torques, although I left off a lot of the details that gets to the harmonic series. How you do that? There's some really fun inductive proofs of the fact that series is what comes out of the math. So let's just go on. I want to quickly talk about springs and then do one final exam problem. Go
Can we
ahead.
hang on for a second?
Mhm.
Like, I'm suspicious of this.
Well, you should be.
This doesn't seem right to me at all. But I can't. Like, I'm suspicious that you said it only takes the 5th block to reach an overhang of 1, but you didn't draw that.
That's right. But you can see. I think
I'm
you can see just from what I
bullshit, I think, but I can't. I don't know how.
well, you can see from what I drew that I'm getting pretty damn close to an overhang of 1 there, right? It's not going to take too many little more segments. But are you saying, maybe you're expressing your intuition that 1 ought to be the absolute maximum? That's a reasonable intuition, right? Is that what you're saying?
Well, it just seems obvious that at some point the center of gravity of the blocks on top of the first block, once they're to the right of the edge of the first block, it's going to fall over.
Right. Once it's to the right of the center of gravity of the first block?
Once it's to the right of the edge of the first block.
Okay. Yeah, and I think maybe I'm not sure I understood what you mean by that, but I think that part of the thing, and this part of the beauty of this as an example, is the need to really think about systems, right? You get that first block balanced on that top block balanced on the one underneath it, and then we just take that thing and we ask, okay, how can I balance it on a third block? And now that you've done that, you just take that thing and you say, what do I need to balance it on a fourth block? So once you have made the top one balance, you're done, right? The only thing you need when you add that fourth block is to make sure that it supports the system. You can glue those top 3 together at this point because you've already ensured that they're okay. So now you're just taking a weird 3 blocks glued together system and you're saying, how far can I move it over? Does that help at all?
I don't know. I feel like there's some sorcery involved.
Yeah, and I think the problem is that in practice, it is really hard to get it even to overhang by 1 full block, to make the overhang be 1. Try it with dominoes sometime. I haven't for a very long time. And I suspect that if you can get past an overhang of 1, you probably won't get much further. But you should be able to do that, right? If you have 10 dominoes, it shouldn't be too hard to make them overhang just practically by 1. And maybe that, at least once you get past that idea that the top block can be sitting above nothing, because I think that's the intuition. That's the weird thing, is that you kind of have this idea, well, under no circumstances could that top block be completely out there over the air. But it's not. It's just being supported by the one underneath it. That's the important thing to remember. Okay. So let's move on then. I just a quick introduction to springs, a one slide introduction to springs, then we'll move on to the final exam problem here. So springs are characterized by a spring constant that tells you how much force it applies, either as a push or a pull, when it's compressed or stretched by some amount x. So this spring force F, I should have put S there. Maybe I will. Well, yeah, I think I will. There, I changed it. If you refresh. The spring force S is just K times X, where K is the spring constant. Springs that are reasonably stiff won't stretch noticeably if you hang them, like I've shown there, at the left side of that diagram. If you just hang a stiff spring, it won't stretch under its own weight. Now, we have lots of experience, I think, with springs that I would call are stiff and springs that aren't. You hang a slinky from a ceiling, and it stretches itself, right? There's no, it is not a stiff spring in any way, shape, or form. And yet a lot of springs that you encounter certainly are springs that don't stretch noticeably under their own weight. That doesn't necessarily mean that they don't weigh much. We often in physics will talk about weightless springs or massless springs. I'm trying not to use the word mass either just yet. But all we really mean is a spring that is stiff enough that its weight doesn't matter. A car spring, a suspension spring in a car, is not a light spring, but it does not stretch under or compress under its own weight in any noticeable fashion. It's a spring, it's a heavy spring that's meant to support much heavier things. And that's kind of what it means to be a stiff spring. So stiff is always a relative thing. It has to do with the intended application. But if it is stiff, it really means its intended application is to exert forces that are much greater than its own weight. When I hang a spring like that from the ceiling, it's exerting a force downward on the ceiling. The ceiling is exerting a force upward on the spring, equal to its weight. And if it's a stiff spring, that's all that will happen. The spring will basically just sit there. But now if I apply attach a block to the bottom of that spring, and if the block is heavy enough, if it needs to be in the range that the spring is designed for, then the spring will stretch a little bit. If it's more than the spring is designed for, you might end up with a wire, right? You might not have a spring anymore. You do what we call exceeding the elastic limit of the spring. And it's really easy to exceed the elastic limit of a slinky. I think we all, as kids, had slinkies that ended up being kind of former slinkies because you ended up screwing them up by pulling on one part of them too hard or whatever, destroying the flimsy elasticity of the slinky.
John,
But in this case, yeah, go ahead.
before we get too far from the block question that Andy was asking, can I
Yeah, go
comment
ahead.
on that question, the overhanging blocks?
You've been thinking about it while we talked about springs, so it must be a good one.
Yeah. So there is an assumption here that's critical, and it's an assumption we've talked about a lot, and that is the compressibility. If you assume that pressure compacts matter, then this tower will have a secondary problem, which is that it will lean. Every time you stack blocks in this way, where you're stacking them more on one side than another, you're putting more pressure on one side than the other. And unless you think that matter does not compress,
Let's not go there.
you've got a falling down, you've got a Tower of Pisa problem where this thing is going to lean.
I think that's a good point. I mean, I'm just going to say that you raise a really good point, and I should have said that myself. That's right. When you start stacking, the 4 blocks on the 5th and the 5 blocks on the 6th, each one that you introduce from below is going to have more and more pressure on that edge, and that's going to make that edge compress a little. It's going to introduce an angle which will cant the top part of the tower out over the void. So yeah, you're exactly right. I have nothing more to say.
What I'm trying to point out is that this is not an infinite series. This
Yeah,
series is bounded
this is, and I think really
by the
it's,
physics of compressibility.
yeah, that's right, and a lot of other things, including the physics of no way to have no breeze in the room, right? The situation we're talking about is what happens if you have absolute perfection. Every single block is infinitesimally away from toppling on its own. There's nothing, there's not a breath of air, there's not a bit of compression, just as you say. That's an important point too.
This is why you should not have math departments, because as
Yeah,
soon as you put the mathematicians by themselves, they they become untethered.
yeah.
All right,
No, that's,
strings.
I still love this example because it's just so fun to think that, if you could do that perfectly, and you certainly can. As I say, there's no question you can get a full block overhang. I say there's no question. I don't remember if I've ever done it, but I'm quite certain that you can do that. And that all by itself is pretty fun. The fact that theoretically you get to this arbitrarily large overhang has all sorts of reasons why that's not true in practice, but it's still kind of a fun mathematical result.
Well, I have some real world data from my entire childhood, which frankly is extended, of stacking blocks.
Are you stacking blocks
trying to
right
get-
now, Andy?
Trying to get trying to get a block completely to the right of another block, and it never worked. And I've tried every conceivable configuration of that.
Really? Okay, that's interesting to me. I can't swear that I've done it. I kind of feel like I've done it. But it'd be very surprising to me if you couldn't do it. If you had a nice set of dominoes or a nicely, set of milled rectangles somehow, especially if they were, metallic rectangles. It's kind of hard for me to imagine that you couldn't do that with, say, 10 such rectangles. But I might be wrong. We got to try it.
A set of very expensive machined parallel
Yeah,
blocks.
yeah.
But then they stick to each other for different reasons. So because
There's that too, right?
So that's not fair.
Not fair. Yeah, that's right. Anyway, so we should do that experiment, right? We should do our own research. You've done it. I guess I need to do it. So let's get back to slide 13. So what I'm showing there is I'm just imagining, and this is kind of an analog of what we did last week with stacked blocks. Suppose I take 2 identical springs, 2 just like the one that was hanging by itself there, and I hang a 1.2 pound weight from the top one, and then I hang another spring from the bottom of it, and another 1.2 pound weight from the bottom of it. And let's just suppose that what I find is that the top spring stretches by 2 inches. If it does, then I assert that the bottom spring will stretch by 1 inch, because after all, the top spring, thinking about systems, if I look at the system consisting of the 2 blocks and the spring that connects them, then that system has a weight evidently of a 2.4 pounds, because we know that 1.2 pounds must be significantly more than the weight of the spring. The spring is stiff enough that it didn't stretch under its own weight, but it clearly stretches under the weight of 1.2 pounds. So the weight of that lower system is about 2.4 pounds, and it's going to stretch the upper spring by some amount. The lower spring is only supporting the 1 block, so it's going to stretch by half as much. So if the top spring stretched by 2 inches, then the bottom spring will stretch by only 1 inch. And I can tell, so I know that for sure, just from the math, and I know that this spring has a force constant of 1.2 pounds per inch. And that's a nice thing. And that means that if I compress that spring, it will push out with a force at both ends. If I tried to compress that top spring, it would now push up on the ceiling with a force of 1.2 pounds if I compressed it by 1 inch. And it would take me 1.2 pounds of pushing to compress it by 1 inch. The force at each end of the spring is just the force constant times how much it's either stretched or compressed. And then we just have to remember that compressed springs push and extended springs pull. Right? So that's all I really have to say about that. I just wanted to get that idea of a spring constant so that we could use it in the final exam problem. But any comments on that? Okay, so let's do the final exam problem. So
That's
this is
what
kind of,
every physics teacher does. They give us the easy cases and look at the final exam. Jesus Christ.
but I'm going to take it, but I'll do it for you. How about that? How many of your teachers ever did your final exam problem for you?
Yeah, after they grade the papers, yeah, all of them.
Okay, so the final exam problem is problem statement. The block in that diagram moves at a constant speed across a frictional surface. I should have said frictional horizontal surface, but you can see that it is, unless I'm tricking you, which I'm not. Pulled by a spring at an upward angle, find the amount of stretch in the spring. And I'm showing you the values of several things. I'm giving you the spring constant, I'm giving you the weight, I'm giving you the kinetic coefficient of friction, which is important because this block is moving. It's not static. And I'm giving you the angle and I'm giving you the speed. So I'm giving you all of that stuff. And so a few questions before we go on. That's the entire problem statement. Now, hopefully, if I were really giving this as a final exam, I'd probably go through that problem statement with a fine-tooth comb and make sure I haven't left any ambiguities. I'm not sure I haven't here, so feel free to point them out if you think there are some. But there are a few questions. So is this a situation of static equilibrium? Notice that that block is moving. And
So
while you're
how do
thinking,
we define static equilibrium? A equals 0 or things not moving?
well, remember, static equilibrium is defined kind of in terms of Newton's second law. An object in motion or an object will continue in its state of motion or rest unless a net force is applied to it.
Yeah, so A equals 0.
Well, so I really, you know how bad I want to avoid the
Oh,
word
you want to avoid the
acceleration
curse word.
so
Okay,
so much that I don't even want to
great.
say the word a.
Okay. No A's. If the speed is constant,
There you
it
go.
means that nothing is affecting that block during the phase we're watching. Because
No,
according to third law of Newton, if things are staying still, then they stay still.
first
And
law.
if they're moving, yeah. So if it's moving at constant speed, we know that the net force total is not changing. So we're
There you
safe,
go.
assuming that.
There you go. Right. And you notice how nice the professor was in bolding and italicing the word constant so that you couldn't miss it. So you wouldn't make the mistake of thinking it might be
So he could
changing
scold
its
you
velocity.
afterwards. So he can say,
Sorry.
I made it bold and you didn't pay
Italicizing.
attention.
It's
Italicizing.
italicizing.
Hold on,
Yeah.
Benjamin. Let Sam go first, and then we'll get back to you.
No, but Benjamin and I have both cringed and corrected you saying italicizing, not
Oh, sorry.
italicing.
Did I say italicing?
Yes.
Oh, God.
I have
Okay.
no idea why you would say such a thing, but you did.
I'm so at home amongst you nerds. This feels so warm.
Okay. Okay. So yeah. So that's good. So it is a case of static equilibrium, and I told you we were going to get back to that, right? The thing I think you said, Shamash, or something about, or maybe it was Sam. Sam, I guess, said something about moving on the wedge. Here's a moving thing, but it doesn't matter because it's not changing the way it moves, and we'll have more to say about that at the end as well. So there's that. How many forces are acting? I notice I have gone to the trouble of drawing the little dotted line around the system that we're going to analyze. How many things touch that system? That's really the first question.
How many things or how many forces? You're cheating
So
now.
so let's just start with how many things touch that system.
2 things.
2 things. And one of those things is a surface, right?
Yeah.
So how many forces are acting?
3 forces. 1, 2, 3, 4 forces.
4 forces, because we always break surface forces
we
up
have
into
gravity.
2.
Yeah.
Gravity. So there's 2 things touching. That would seem to imply 3 forces, except one of those things is a surface, and we always break up surfaces into 2 forces, 2 components. So that's 4 forces. So we're going to have 4 forces. This is really an important thing. Students really skip this just identifying the contact, counting how many forces, so that when they go ahead and work, they can just come back and say, okay, do I have 4 forces here, right? There are going to be 4 forces. Let's make sure I have them all. So that's that. How does that kinetic friction thing work? And I'll just answer this myself. The nice thing about kinetic friction is it's simple. The frictional force is mu k, the kinetic coefficient of friction times n. There's none of this maximum frictional force. Is it? How does it decide what the frictional force is just mu k times n. In this model that we're using, which is not a perfect model, but it's what we're going to depend on. If the block is moving, it's that. Go ahead.
Isn't it sometimes like mu times v, like relative to the speed? The quicker it is, the hotter the surface gets, so it moves easier, something like that, or harder. I don't know.
Yeah, a couple things there. I mean, there is the question of how speed can even affect the kinetic friction through something like that. But more importantly, when you're talking about what's called viscous friction or dynamic friction moving through a fluid, then it's a very different kind of a thing where the velocity does matter. It's part of the formula for viscous or dynamic
like air
friction.
resistance.
Right.
Yeah.
Right. Go ahead, Ben. You were going to say something too?
I can't remember what I was going to say. Oh, I was going to say I can only see 2 forces, but you know why I'm only saying I can see 2 forces. No,
Yeah,
I do. Let's not confuse people with that. Okay.
Yeah.
It's only 1 force. The other one is fake.
Well, and Ben, in this, you'll be pleased to know that we're going to integrate the principle of equivalence right into this introductory physics course, so that we don't have to. I think it's one of the things I really like to do is to start off right off the bat with gravity being. That's why I'm making this whole point about how weird gravity is, because I want to show you eventually that it's not really that weird. It's just we're looking at things in the wrong reference frame, but it's a good wrong reference frame to look at things in. And that's what we're going to get to when we in 2 or 3 more episodes we'll be talking about that.
Well, why is there a spring at all?
Like, yeah, well, I just wanted to make this hard. That's why.
Because it does make me think like there's going to be some oscillations and wobbliness going on, but I think it could be replaced with just like a string or a I'm not sure.
No, you're right, and yet at the same time, I think I kind of dealt with those objections, although you might object to the way I dealt with them, by saying that the block is moving at a constant speed. If it's moving at a constant speed, I have to somehow be manipulating that spring very carefully to make sure that whatever force it applies and whatever angle it's applying it at don't change, right? That's the only way that velocity is going to remain constant. But it's a good point. I mean, once again, if you just think practically about these things, be very hard to pull on that spring in a way that would make that block move at a constant speed. And yet I'm basically saying I am.
That basically ties in with what Shamash shows as well, which is that in reality, that coefficient of kinetic friction will vary with speed for most pairs of surfaces, right?
Right. And probably in reality, if you were to try to do this, you'd find the block sometimes, just because it's a spring, sometimes that block would stop and then it would have to unstick again. All sorts of nasty things happen as when you can't keep the velocity constant. So somehow I'm magically pulling on that spring so uniformly, moving. I imagine my finger holding the top of that spring. I'm pulling it in such a way to maintain the angle and the stretch while moving. That's a pretty hard thing to do. And yet I'm just telling you essentially that somehow I'm doing it. These are all the spherical cow aspects of physics problems. It's really good to identify them and to be honest about them and to say, that once you learn how to do this with all these unrealistic assumptions, you can come back and do them correctly. The physics doesn't care. It's just do you want to be able to solve this problem or not? That makes you make the spherical cow approximations that we always do. And that's just because you're learning. Okay, so even before starting solve a
John,
problem, go ahead.
before you go on, I just want to say I need to take off. I have a meeting at noon in 5 minutes.
Well,
Just wanted
thanks
to
for.
thank you and say see you all later.
Yeah, good. Thanks for coming, Sam, and I'm glad you're feeling better. Yeah.
Great. Thank you very much.
All right.
Bye.
So a few things to whenever you do a physics problem, the first thing to do is all the things you guys are already doing. You guys are naturals in terms of thinking of practical things that I want to assure you we don't have to worry about. But it is worth thinking about what's going on. For instance, are torques important here? Am I going to get information by writing down a torque equation? And that's kind of a subtle thing. I don't know. What do you think? I think all of you guys probably think of a reason why torques are kind of important. But whether they would change things, I don't know. Anybody want to tackle that
I
one?
I was think that was one of the first things I was thinking about, and I guess I came to the conclusion that since you said it was everything is in equilibrium and you're moving at a constant rate, that I guess it doesn't matter. I mean, it's whatever you're saying is the coefficient of friction is sort of like the effective coefficient of friction for whatever. Like I guess I'm saying that spring could be attached anywhere on that block, and you would kind of get the same results. I think.
Right. That's what I'm thinking about too. And the point is I've kind of shown the spring attached at a place that I think makes it not obvious. If I had attached that spring at the front of the block rather than at the corner, you might start saying, "Ooh, is it going to lift the front end of that block up above and then what happens?" Well, probably nothing because, as you say, I've kind of built the coefficient of friction in. It might tilt up a little bit, but presumably it's not going to flop over onto the back side or anything. If I attached that spring at the back of at the back end of the top, then it would kind of maybe dig in at the front. Maybe the digging in would increase the coefficient of friction. But I've told you the coefficient of friction. All these things are, they are worth thinking about, and then kind of realizing that I've essentially told you not to worry about them in the way the problem is stated. But yeah, no, good points.
In reality, I've dragged a lot of things like this, not necessarily with bungee cords, because that would be even more awkward, but it really does make a big difference in reality,
Yeah.
where you attach it for the reasons of digging in at the front and back. What you haven't talked about here is that the coefficient of friction is independent of the contact area between the two things, which is counterintuitive when sports cars have, so it makes you ask the question, why do sports cars have wider tires, for example? Whereas the first order physics that you're looking at here would say you could put bicycle thin tires on a sports car and it can accelerate just as fast, which in principle it could. And this is second order reasons why this isn't the case, to do with the probability of achieving that coefficient of friction on the actual size of the patch, given the varying road conditions and the way that tires distort under torque and all the more complicated second order effects. So it's worth just noting that you're saying that, regardless of whether it's resting on an infinitesimal point or the whole bottom surface. Area hasn't come up in any of your discussion. Contact area hasn't come up.
Yeah.
Whereas again, in reality, when you do a second order analysis, you do need to take account of area
Yeah. No,
for more subtle dynamic reasons.
that's exactly right. It's why I really emphasized, maybe not even enough, that this model of friction is a model that works pretty well, under lots of situations. Um, Probably would in this situation if this were, kind of a heavy wood block running along, a wood floor, or, with any kind of a material like that. But when you start talking about if it were a rubber block and you attach that spring at the back end, then the digging in at the front would probably be really important. It would change the effective static coefficient of friction. But the fact that I've told you the static coefficient of friction is essentially just saying, I've worked it out, for whatever. That's what you use. So anyway, all good things. So we're going to say, so torques are they important here? Yes, absolutely, practically. But because of the way the problem is stated, you have some problem since you understand, oh yeah, the professor's asking me to ignore all of those things. So that's just test taking skill. How do you think the answer might change if the spring were at a smaller or larger angle? What kinds of things go on in pulling upward at an angle like that? We don't have to answer them specifically, but any kind of quick comments on that?
Well, there is a scenario where the block lifts
Right.
if the numbers match. Like if this is a stiff string and the delta x was big, it could lift up from the ground, which would change the entire regime. You'll have to be talking about something because there's no friction anymore.
If the angle were 90 degrees, could this even happen? I guess it could, right? You
Well,
could
if you have
essentially.
because 5 pounds an inch and you need 20, so you need 4-inch compression or extension. Actually, you need extension, not compression here, and then anything above that, you will get lift.
That's right. That's right. Although at an angle, it's not quite clear what happens. Something, if you want to keep the velocity constant, something else happens. You could imagine that this spring is vertical. It's stretched by just a little more than by 4 inches. So there's zero contact force with the surface, and you're just moving the point of contact. You're just moving the spring to the right at 4 feet per second, and the block is just hanging vertically from it, moving with that velocity. And that would be essentially the same thing as just having it suspended over a surface that's moving to the left at 4 feet per second. Right? Just a simple static holding that mass up. But I was thinking also a little more specifically about the fact that the larger that angle is, the more the force of the spring is reducing the contact force, which is nice, right? That reducing the contact force is nice because that reduces the frictional force. And yet it also reduces the pulling force. So if you were to pull at a lower angle, you might need more pulling force because you wouldn't have relieved as much weight from the surface. So there's an interaction, I guess, is the main thing between how much I lift and how much I have to pull horizontally to make it move at a constant speed. Andy, go ahead.
Well, an interesting problem would be to give the spring like a strength. So like if you pulled it strictly horizontally, you might exceed it might break. But if you lift it up, there might be some angle at which you've relieved enough of the friction down below the breaking strength, the strength of the, and then you can make it work that way. I was just thinking of a way of adding to the problem.
Let me ask everybody for a prediction. Because you could imagine if I changed that angle, so if I made that angle smaller, would the stretch of the spring be greater or smaller?
Keeping V equal 4.
So the problem is, everything in the problem is exactly as it is, but suppose I made the angle 30 degrees. would
Yeah.
the
So
answer get smaller, a smaller stretch or a larger stretch?
okay, give me a sec.
Doesn't it depend, John, on whether you've got past the kind of point at which the benefit of lifting the block off the surface and reducing the friction is going to kind of weigh against the lost,
Exactly.
the lost forward acceleration. Well,
Exactly.
moving force.
There's clearly
There's a
and
balance
the
point.
that's the point, is there are competing effects, and those competing effects are going to be absolutely central to the final point I make a few slides down here.
Yeah, if you had a very heavy block and a very low friction, then lifting up would you would stretch the spring. But if you had a very light block with very high comparatively higher friction, then it would be the opposite. I would think it would.
But the friction
There's a
depends on the
balance of
weight of the
things.
block. That's the thing here. Like the heavier the block, the more the friction.
So you're going to
Right,
be
but it also depends
Yeah,
on the
there's
coefficient of friction. That can change too, depending on the nature of the surfaces.
yeah
Right?
that wasn't the point I was making. Well, John will get to it in a few slides, I think.
yeah,
You're suggesting,
yeah,
John.
yeah. I beg you not to look ahead unless you want to know the answer now, because it's fun to test your intuition on this as to what you think would happen, whether I would have to stretch the spring more or less. That's really an interesting question. Just that even if you don't commit to anything here, think about what you think. If I were to make that angle 30 degrees, would the answer to this problem be a smaller stretch or a larger stretch?
I'm guessing smaller if you want just my intuition. I want it
Okay.
to be smaller.
Anybody else want to offer a prediction?
I want to say it depends on the relative weights and frictions
You're not
involved.
allowed to say it
but they could all.
depends.
It
You
could
just
be.
have to answer.
This could be. I
Jesus
know,
Christ,
but
these nerds, you just can't.
Can't get them to commit. Just
think
commit,
you
Andy.
can peg different corners of the thing, but it could also be a thing where everything just cancels out and it's always the same no matter what you do. I haven't done the math.
Okay, well, we'll get to it. It's really a good one, though. So how would the answer change if the block were moving faster or slower or not at all? And I think we've already answered this one, right? Static equilibrium in any situation. So you probably anticipate correctly at this point that the velocity is completely irrelevant. Only the fact that it's constant is relevant in the theoretical realm in which we're dealing right here. How would the answer change if the block weren't moving at all? Well, okay, so that's a little more interesting a question. How would it change if it weren't moving at all?
So we'd
I
be
guess-
solving for only one point instead of keeping sine theta and cosine theta, because as the block moves forward here, theta becomes bigger and bigger, so it's a differential equation. Whereas if we just take the snapshot and solve here, that's an easier problem.
Well, I'm not sure what you mean by that exactly. If the
Okay.
block weren't moving at all, there's one important difference now. And that is that it would...
I think I answered, because here what we're trying to solve for is an equation of motion, right? This is I don't.
No.
What is it that we're trying to
We're
solve
just
for?
trying to find the stretch of the spring.
At that instant.
Well, but this instant is any instant, right? This is happening, right? The situation that you see right now continues as it moves to the right.
Yeah, but the spring is not moving uniformly at v equals 4 with the block, right? The spring
It better
is fixed
be.
to us.
Oh,
The spring is fixed somewhere, and then that's what I understood.
I
no?
see what you're saying. No, I anticipate. That's a good question. The fact that I say that the speed is constant can only be the case if I am continuing to supply these forces, right? It's not going to be constant if the point of attachment of the upper point of attachment of that spring is fixed, because now the force will change. And if the force changes, I'll no longer have a force balance. So
yeah,
I'm gonna,
but then because you're keeping the velocity fixed, you cannot play with friction. Okay, got it. Yeah, sure.
yeah, the only way I can make that happen, I think, I mean, I challenge you to think about some way, but the only way I can make this happen is if I'm moving the
The
top
whole thing
end
is
of that
moving.
spring,
Yeah.
the whole thing is moving, right?
Yeah.
Yeah. Okay, but if the block weren't moving, now we'd be talking about static friction. right? And then I wouldn't be able to answer the question because as long as I don't stretch the spring too much, it'll just sit there. So there'd be a maximum stretch I could calculate, but there wouldn't be. I couldn't answer the question, what is the stretch? It could be zero, it could be a little bit, it could be up to some maximum amount that would make the block start moving, which would mean that it's no longer static. It's no longer static equilibrium. But so that makes it a much more, that's a more complicated question. And it's part of the reason I did make the block move was to avoid the difficulties of static friction again. Okay, so let's move on. We've spent enough time talking about all that. So we draw the free body diagram. We've already said there are four forces. We know what they are. There's a spring force upward at angle theta. There's a normal force perpendicular to the surface. There's a frictional force, presumably to the left, right? Frictional forces always oppose relative motion like that. Kinetic frictional forces anyway. Static friction, not always, interestingly. And then there's a gravitational force, the weight. So I've got four forces. And I've shown you three ways of drawing the vector sum. The vectors have to add up to zero. The first one I like best because it makes this nice open polygon. So if you want, start anywhere you want, say at the base of the normal force, draw the normal force. Then I bring in the spring force. I put its tail at the tip of the normal force. I bring in the weight force. I put its tail at the tip of the spring force. And then I finally bring in the frictional force. I put its tail at the tip of the weight force. And I have to get back to where I started. That's what it means for those four vector forces to add up to zero. But I could have drawn it other ways. And I'm showing you two of several other ways that you could draw that force diagram. All of them end up making a closed path, right? Wherever you want to think of starting, you come back to that point by adding the vectors tail to tip, tail to tip, tail to tip, etc. But I'm going to use the one on the left because it's kind of the simplest one to see. So there they are. And you can kind of see right away where we're going to go. There's two upward things. There's the normal force and part of the spring force. And then there's the downward force of the weight. Those have to balance. And there's sideways forces. There's a force to the left from the frictional force, and there's a component of the spring force to the right, which has to balance that spring force. The nice thing about vectors is you can just think about what are called the components. And I am really glossing over. I mean, normally in an introductory course, we'd spend 2 or 3 days talking about the mathematics of vectors and breaking components. I'm just talking here intuitively about these things, but because I don't want to spend time on that. If you want to learn more about it, happy to talk with you privately or just send you somewhere on the internet to learn how to do these things. But let's just take that diagram on the left and go to the next slide, slide 16, and we'll just write down and solve the force balance equations. Before I do that, notice I've reproduced the force diagram over there at top right, but underneath it, I've taken that spring force in particular, and I'm showing you these two components, as we say, the horizontal part of that spring force and the vertical part. If I were to have a vector to the right and add a vector upward, I could get the same thing as that S. I would start from the base of the S and I'd end up at the tip of the S. So there's an upward force, which is S sine theta by trigonometry. You get the side opposite the angle, theta, by multiplying the hypotenuse times the sine of theta. And then you get the side adjacent to the theta by multiplying the hypotenuse times the cosine of that angle. So that's what those components are. And with that in mind, then I can quickly write that the force balance equations tell me that in the vertical up direction, I have positive N plus s sine theta minus w has to equal 0. Basically saying the two upward forces, n and s sine theta, have to add to equal the weight, but I'm just simply adding those three vertical forces, one of which is negative, to get the 0 that I need to get for static equilibrium. And in the horizontal direction, it's even easier. I just have one positive force, s cosine theta. I have one negative force, f, and they have to add up to 0. But then also remember that I have a couple of auxiliary equations. I have an equation that relates the frictional force to the normal force, that is, that it is mu k times n, and I have the force that tells me the spring force in terms of the thing, after all, that I'm trying to find here, right? How much is that spring stretched? X. So there are 4 equations there that I have mustered, and I have circled the things in those equations that I don't know. I don't know the normal force. I don't know the spring force. I don't know the frictional force. And I don't know the stretch of the spring. I don't know any of those 4 things. You'll notice that some of those things show up twice. I've circled with dotted lines things that show up again, like the S shows up again. I don't want to think of that as another thing I don't know. I already counted it as a thing I don't know. So I circled those 4 things in bold red, or in, non-dotted red, just to say there are 4 things I don't know, and I have 4 equations. And if you learned anything from algebra, you know that generally, not always, but if you have 4 equations in 4 unknowns, you ought to be able to solve those 4 unknowns. And the nice thing about going through this process of identifying the unknowns where they show up is it allows you to kind of come up with a strategy for solving the equations. In this case, what you want to do is you want to eliminate unknowns that you don't care about. And one of the nice ways of quickly eliminating unknowns that I don't care about is to use those 2 auxiliary equations to get rid of the frictional force and the spring force. I'm just going to substitute for the frictional force mu kn, and I'm going to substitute for the spring force kx. And if I do that, substituting those 2 things in the first 2 equations, I end up with, take the top equation, I get n plus, rather than s, kx sine theta equals w. And if I substitute the frictional force into the second equation, I get kx, not the frictional force. If I substitute the, did I say that right? Substitute both things, substitute both the friction and the spring force into the second equation, I get kx cosine theta equals mu k times n. So now I have 2 equations, but those equations, I've eliminated the frictional force and the spring force from those 2 equations. So now there's just 2 unknowns. I have 2 equations in 2 unknowns, n and x. So now I want to eliminate n by solving one equation for n and sticking it in the other. This is a bunch of algebra here, but it has a huge payoff by doing that. Students often get flustered because they want equations. They want to know what they know. So they too quickly plug numbers in. You plug numbers in, now you're carrying numbers around. You don't put units in because you don't want to have to worry about them. So you just put numbers in, you end up with equations that end up becoming really problematic. Whereas doing it this way, by simply taking the second equation, solving it for n, sticking it in the first equation, just the opposite. Solving the first equation for n, that would be w minus kx sine theta, and sticking that in the second equation, I get kx cosine theta equals mu k times w minus kx sine theta. And the nice thing about that equation is there's only one thing in that equation I don't know, and it's the thing that I'm trying to find. And that's not an accident. I designed that by keeping track of the things I don't know, trying to eliminate the ones I don't care about, and keeping only the thing that I don't know and care about. So at this point, I have one equation in one unknown, and it's just some algebra to isolate the x in that equation, and you get a relatively complicated looking equation. Mu k times the weight divided by the spring constant times this combination of the angles and the spring constant, cosine theta plus mu k sine theta. That's kind of a complicated looking equation, but there it is. And at this point, that's an equation that gives me the thing I'm trying to find in terms of nothing but things that were specified in the problem statement. So sorry if that one was a little overly too much math, but this kind of thing has a huge payoff if you can learn to kind of monitor your progress, the things you don't know, not just stumble blindly in the algebra saying, okay, what if I solve for this and stick it in there? You have to have a strategy, and part of the strategy has to do with keeping track of the things you don't know and looking for obvious ways to simplify by getting rid of things you don't know and you don't care about. So I take that final result on slide 17 and just plug in the numbers. I get the stretch is 1.58 inches. Right? There's the numbers. You get 1.58 inches. Aren't you happy to know that that spring has to be stretched by 1.58 inches? Kind of a letdown. The actual number is kind of a letdown. The equation itself is much more interesting than the answer, because that answer is just what you get for some specific values of mu k, w, k, and theta. But now I can explore what happens for different, because I have the equation in symbolic form. I can ask other what if questions. What if the angle were lower, 50 degrees? Shamash guessed that the amount of stretch would get smaller, and he was right. Ta-da!
In your face, Andy.
Wait. All, in my all I see is x on one side, and I see a theta on the other side. So I think I'm right too.
Oh yeah, Mr. It depends.
So it does depend, right? The answer does depend on those other things you wanted it to depend on. But of course, the only thing I asked is what would happen if you change the angle. Because that's the only thing that's interesting, right? If you, in fact, you can look at that equation and see immediately that if you make the spring stiffer, x will be smaller. If you make the weight bigger, x will be bigger. It's not quite so obvious what happens if mu k changes, and not quite so obvious what happens if theta changes. But w and k only appear as multiplicative factors in the numerator or denominator of that thing. So if w gets bigger, x gets bigger. If k gets bigger, x gets smaller. And that should make total sense, right? If that doesn't make sense to you, you need to check your intuitions. So what if the angle were 70 degrees? Well, not surprisingly, since the stretch got smaller when I made the angle smaller, if I make the angle bigger, it shouldn't be too surprising. It actually should be a little surprising maybe, but it's not too surprising that the x gets bigger. But better yet, I don't have to just like calculate it for different angles. I can graph the amount of stretch as a function of x. I can take this formula and put it into a spreadsheet, generate a bunch of data for all sorts of different angles, and then graph it, as I've done over there on the lower right. And when you do that, you see out there at 60 degrees, indeed, when the angle gets smaller, the stretch gets smaller. And when the angle gets bigger, the stretch gets bigger, all the way up to 4 inches. And we saw that Shamash brilliantly mentioned the 4-inch thing before. If you pull at 90 degrees, then you're going to have to make this happen, you're going to have to provide enough force to lift that weight off of the surface. And that takes 4 inches of stretch to get 20 pounds of force out of that spring. So that all makes sense. But the interesting thing happens down there at lower angles. When you get to low enough angles, it turns out the stretch minimizes and then starts increasing again. And this is what Ben was talking about when he mentioned the competing factors. Because at some point, when you start pulling at a low enough angle, you stop losing all benefit of lifting the weight and reducing the frictional force. And now you have to supply additional motive force to overcome that frictional force, which has now gotten to be pretty large because all 20 pounds of that weight are pressing into the surface. And the most amazing thing, of course, I can just look at that graph and see that it happens somewhere above 15 degrees. But you can deploy calculus, and I won't even talk about how, but it turns out you can show that that minimum angle happens when the angle is the arctangent of the kinetic coefficient of friction, which looks very much like the formula we found in a very different looking problem involving a block sliding down an inclined plane, except that in this case it's the kinetic coefficient of friction. If I put in arctangent of 0.3, I get 16.7 degrees. And so that is the place where the minimum stretch will do it. And that should make total sense to you if you've ever done. Ben's pulled blocks with strings, and he knows that you want to lift up a little bit, right? You don't want to lift up so much that you're having to apply all this force to lift the thing, but you want to kind of lift. You certainly don't want to pull down. Pulling down is going to be the wrong thing to do because now you're going to be pulling it down into the ground. In fact, I should have graphed this for negative angles. What do you think that curve would do if I had negative angles? Amazingly enough, the same formula will still work, and that curve will continue to increase as I go to negative angles because of the fact that now I'm pulling that block down into the surface, needlessly making the friction larger as I try to move it. Okay.
People who do these hardcore climbers who take all their stuff and they go to Everest Mountain or to the North Pole or something like that, they should do the math like this. But I think they know it intuitively,
right?
Because they have their package like really lagging behind them, like 3 or 4 meters lagging behind them. And if you do that triangle, like if you imagine it, it's almost something between 20 degrees and 15 degrees, and this makes it a lot easier, and they know it. It makes it easier for them to carry their luggage and go, or drag their luggage, I should say, behind them.
So I may have missed something there. There is this weird. I should have had one more example, and maybe I'll mention it here. Maybe I'll just mention it right now. There was when I was growing up, these people decided to make a ship out of a big oil drum. I think it was, maybe like 20 feet long, 3-4 feet wide, or something like this. They built a pirate ship around this vertically placed oil drum. The idea was that it would sit down deep in the water, be able to support a giant, not giant, but maybe 20 or 30 foot model of a pirate ship sitting up above it. So it provided the buoyant force. You have this big vertically placed cylinder with a pirate ship model built around it. But then they thought about it and they thought, oh, that's going to be pretty tippy. I better put some keel weight in it, right? I don't know if it had basically the oil drum was the keel, but they wanted to have a lot of weight down there at the bottom so that the thing wouldn't just fall over in the water, being a vertical cylinder as it was. And they thought, Oh, better yet, let's hang that weight from a long cable. So they took, I don't know how much weight, probably a ton of weight or something, maybe definitely half a ton, I would think, and hung it from the bottom of this cylinder. And once again, I don't know how long, but let's say a 20-foot chain going down to this heavy weight, so that it would be way down there and really pull the ship over. And of course, the problem is that gave the boat a draft of 40 or 50 feet. So the ship wasn't able to sail anywhere that didn't have at least 40 or 50 feet of water without this weight hanging from the bottom of a 20-foot cylinder dragging on the bottom. And that's exactly what happened when they set out they left Newport Harbor, went out the jetty, intending to sail around the world in this thing, and quickly got hung up on some rocks at the end of the jetty or something. I don't remember exactly what happened. And the funniest thing about that, maybe I'll leave it to you, is why hanging it from a cable was really a stupid idea. Any ideas on that? It really feels right? It feels like the right thing to do, to hang that weight from a cable so it's really far down there, really tugging on the cylinder. But the problem is that the torque that it provides is exactly the same as if that weight had just been placed at the bottom of the cylinder. Because after all, the chain is simply applying a downward force that's roughly equal to the weight of that ballast at the place where the ballast could have been if they just placed it there. There's no difference in the torque supplied
I didn't
by
understand.
putting it there.
So you had a cylinder and it's submerged in water, and the inside of it is empty, right?
Right, buoyancy
And then
there.
and then they decided, instead of making that their ship, they decided to, okay, let's put a weight that is about a ton and hang it from a chain from the bottom of it, right?
Right. That what they knew for sure, and they were right about this, they needed a lot of weight down there to keep all that buoyancy from just flopping the boat over on its side, right? You need to have in the nautical terms, you need the center of gravity to be below the center of buoyancy. So you need a lot of weight underneath all that.
You need a writing moment.
A writing moment. Okay. Yeah, there you go. That's what it is. Right. So that when it tips to the side, the buoyancy and the weight provide a writing torque on the thing. So you do need that. But
So
the problem is,
their intuition was, if you put the weight way below, you are making the center of gravity way below the buoyancy center.
I think that's exactly right. I suspect that's where the intuition comes from. Go ahead, Ben.
Well, it's dumb though, because the bottom of the boat doesn't know whether it's connected. It just feels the force from the chain. Whether or not
Right.
the chain, however long the chain is, makes no difference, right?
Right.
All the way down to zero.
Go ahead,
The
Andy.
actual sailboats do this by having longer keels.
Right.
And then also by, like more high performance sailboats have most of the mass at the bottom. They have like a bulb keel in a very small, light,
Right.
but strong fin. Right. And that makes the whole boat feel stiffer and stuff. So, but it's got to be rigidly connected. If it's by a chain, then the chain could be 0 feet or 100 feet. It doesn't make any difference. Just dragging around a bunch of chain for no reason. That's dumb.
Yeah, that's right. I think, it's interesting. Shamash mentioned that. I hadn't thought about it. I think the reason it intuitively kind of is appealing is that idea that you're putting that weight so far down. But as you say, Andy, the important thing is that the weight move over to the side when you tip over. Otherwise, that weight hanging from the chain just ends up applying the same force to the bottom of the cylinder, the same downward force to the bottom of the cylinder that you'd have if you just put the weight at the bottom of the cylinder. Hanging it from the chain makes no difference at all.
They didn't actually build this, did they, John?
They did. They built it. They sailed it out of the jetty.
How do you get as far as building it without spotting that? I get the idea of drawing a sketch. I get the idea of drawing a
There
sketch
are
and
so
looking, or
many
somebody else looking
examples.
at your sketch and saying that's dumb, but wow.
There are so many examples of ridiculous boats being built. Like people have, like, yeah, just completely wasted dreams.
And sailors
But yeah,
are crazy, right?
they're a weird bunch. Yeah.
They do these things, and they're fearless, right? It's like the guy who built the rocket to launch himself up and see if the Earth was curved.
There was this guy in the Bay Area a few years ago who built this like crazy trimaran out of like tubular aluminum, and he welded it. It was like a younger guy too. I mean, I'm sure he spent his whole inheritance on it, or you know, future inheritance. And he got it out the gate and was sailing down the coast, and like this. I used to be in a bunch, you know, pre-Clubhouse. I used to be in a bunch of like sailing forums, and everybody was looking at this thing like, no way, don't let this guy put this in the water. But he was rescued somewhere off the coast of like Santa Cruz in a sinking boat, and but he got out. Anyways, but can we go back to the equation and that curve?
Yeah,
This is fun. I mean, I would love to talk about boats, but that curve. Okay, so you have this curve. You mentioned the weight and the what is it, the mu k as like kind of like just multiple.
Oh no, the weight and the spring constant k.
Okay.
Yeah.
But okay. So the friction coefficient, that's the mu, right? Now,
right.
I have to go back and forth to look at it. So that's in there being multiplied by that sine theta. So if that changes, how does that change the graph?
Yeah.
Like,
so you can see
this curve is based on a certain weight and based on certain numbers, and you're varying the God dang it, I just moved it. So I'm just I can't imagine it's going to change the nature of the curve that much, but maybe it'll shift the minimum around.
That's exactly right. It's really the only thing left, because we know that it peaks at the weight over the k, right? When theta is 90 degrees, you just need the spring force to equal the weight. So that's the stretches the weight divided by the spring constant. But then it drops from there. That should make sense right now that we know that as you decrease the angle, the amount of stretch, the amount of spring force needed gets smaller and smaller. But you can see from the calculus result there that if mu k gets bigger, we will have a larger angle, because arctangent is an increasing function of its argument. As mu k gets bigger and bigger, the arctangent of mu k also gets bigger and bigger. So larger kinetic coefficients of friction will lead to larger angles at which a minimum spring force is necessary. So that curve will just have its minimum moved to the right if you increase mu k and vice versa. And it will change. Of course, the values will change as well depending on the details, but the most important thing is just that the minimum moves to the left or right. Okay. So I'm done. I'll just mention, we can continue talking, but looking ahead, we already saw a hint of this. So static doesn't mean not moving. How could it? Since motion itself is in the eye of the beholder. Newton's first law basically says that. Motion's not really a thing. That's just looking at something from a reference frame that's not the same as the thing itself. If I move with this block in the last example, then it's just a stationary block with a surface that's sliding by underneath, pulling it to the left with a frictional force. And that's the same thing. It is exactly, the physics is identical. The physics can't depend on velocities. So next time we're going to talk about Galilean invariance, which is just that the laws of physics are the same in all reference frames moving at constant velocities relative to each other. So I can always change if I don't like, You know, if I don't like the looks, if something looks complicated just because of a velocity, I can always simply change all the velocities to be in a different reference frame. And there's nothing that changes about the physics. So once we've kind of established that, that won't take too long. We'll talk about that. Then we'll ask, well, what happens now that we know that? What happens when an object is not in static equilibrium? What happens when a non-zero force acts for some interval of time? And Newton's second law answers that question in a perfectly obvious way. The way Newton himself expressed his second law was essentially to say that the velocity of an object subject to a non-zero force will change. And the amount of the change is one, directly proportional to the force. That should make total sense. It's directly proportional to how much time that force acts. That should make total sense. The only thing that might be new is this idea of inertia, that the amount that the velocity changes will be inversely proportional to some measure of how much inertia the object has. So if I exert the same force for the same amount of time on some object that for whatever reason has a lot of inertia, whatever that means, then its velocity won't change as much. And I'm trying to make it sound mysterious. It's not mysterious. We all know that if you push on a big, heavy, massive, whatever word you want to use, object, it won't change its velocity as much as if you did the same thing to a smaller object. But there is something mysterious about that inertia. I don't want to underestimate how mysterious the idea of inertia is.
Oh, it's very mysterious.
Yeah, even if we all understand it intuitively, right? We do have a really good understanding intuitively, but it is really mysterious. Yeah. So now I'm really done. We can talk about we can talk about that equation again. We can talk about others. We can even talk about. No, we weren't. We're not going to talk about getting the data or anything. But Benjamin, if you want to try to squeeze that in somehow, I know you're itching to.
So things are getting weirder and weirder, and I really appreciate being here. I always enjoy doing some Newtonian mechanics. So. Thank you, John, for that one.
Thanks.
Hopefully we're going to get deeper and deeper. So please don't stop this. If you're thinking we're getting bored, we're not.
Well, I really appreciate you guys sticking with me through these last couple, because I think they were, I think it's not everybody's cup of tea, even though I think there really is fun stuff. Like when you learn to do basic physics problems correctly, that is to say symbolically, understand how not to. If anybody who's taken introductory physics has probably done just what I did as an introductory physics student. Plug things in, you have to get a bunch of equations, start just randomly trying to solve for this and plug into that, and you end up, oftentimes you end up proving that 0 equals 0 because you plugged something in twice that canceled itself out. You cancel terms and you get 0 equals 0. At least you know you didn't make a mistake, but you didn't prove the thing you wanted to. There's all sorts of really frustrating pitfalls that introductory physics students go through until they learn to use the physics to generate equations and then take a long look at those equations to devise a strategy as to how to eliminate variables that you don't know and don't care about and get to the thing that you do know about. And that was kind of a baby step example that we did here. And the payoff is that you end up with a symbolic equation that you can then use to answer lots of questions beyond the, proximate one that the specific problem was asking about. That's the huge payoff.
So what you said there was funny to me, that like proving 0 equals 0, because I remember doing that, because like you listen to your professor and they're always like, oh yeah, you can just take this equation and that equation and put this equation in here. And I'm like, how are you just picking all these equations? So then, when I'm doing homework I'd be like, okay, I'll try that. I'm just going to pick. And then I end up like getting 0. And I was always confused by that. So I think what I was doing there is like, you think you have 2 different equations, but they're really just the same equation.
Right.
And that doesn't count as having 2. So is that like, there's a word for that, isn't there? Like linear independence or something like that?
Yeah, that's right.
I made that mistake so often, and I'm still not.
But it's not just that. I mean, part of it is, as I said, we had 4 equations and 4 unknowns. Generally, that means you can solve, but sometimes you only have really 3 equations. It just looks like 4 equations because 2 of them are linearly dependent on each other, is the language of math. So there's all sorts of pitfalls like that. But more commonly, when you have 3 or 4 equations and 3 or 4 unknowns, and you don't sit down and think about the strategy to solve them, and especially when the equations get more complicated than the ones we were looking at, you can just end up floundering around saying, okay, now I'm going to solve this equation for this and stick it in here. And you end up at some point kind of undoing something. You did something once, and then you kind of did the reverse another time, and then everything ends up canceling. You either just get an equation that you already knew, or you get 0 equals 0, or you get 0 equals 1, which just is, the result of doing that and making a mistake along the way. And it's endlessly frustrating. So devising strategies for solving systems of equations is really useful, learning how to do that.
It's like if you're bad at tying knots, sometimes people think always tying another knot is a better thing. More knots are stronger.
Yeah.
But sometimes you can tie a knot in a way that undoes the first knot, and you end up with a straight string again. It's something like that.
Yeah. There's those great, what's that? There's a great hitch knot that I forget, the thing that cowboys do, right? The cowboys do this great hitch knot that relies on friction to work, but it has this loose end that you just pull on and the whole knot just falls apart, right? So you tie your horse up. It's pretty good. The horse can pull on his end of the string and it just makes the knot tighter, but you can pull on this looser end and it just falls apart because it's not really a knot. It's just a string wrapped around a post rubbing on itself. I don't know if that's related or not, but I love that knot.
Sounds like a slipped clove hitch.
I can't remember what it's called. I think it has a name like a, cowboy knot or a horse hitch or something. I don't know. Maybe that's another name for it. I don't remember that name. I have to remember how to do it because I used to be really good at tying it. I would amaze my friends. Okay, let's see. Oh, and let me just mention again. So beyond what I said about looking ahead, the thing I want to really try to do for Ben's, Ben's not here anymore, but and Ben appreciates this thing as well. I think a lot of us do, is to try to really embed the principle of equivalence into what I'm doing. So I've been kind of careful not to talk about inertial frames. When I finally do introduce inertial frames, I will do so by making the claim that an inertial reference frame is a reference frame in which objects that move at constant velocity have no force acting on them. That's what Newton said too. But Newton had a different idea about inertial frames than we're going to have. In an inertial reference frame, an object subject to no force will move at a constant velocity. And what that will turn out to be is a freely falling reference frame. A reference frame subject to no force is a reference frame in which an object subject to no force is an object that has nothing touching it. So I've been carefully talking about weight as being a force that happens without touching in statics. But we're going to see that to really try to make the most of nice simplifications that come from the relativity, from kind of tacking a little relativity on top of Newtonian mechanics, is to define inertial reference frames as reference frames, freely falling reference frames in which the only forces are forces of contact. If nothing's touching an object, then it moves at constant velocity. And that means that in an inertial reference frame, there cannot be a gravitational force. In an inertial reference frame, weight is always zero. If you're weightless, that's because you are in an inertial reference frame. That'll be the picture that I emphasize repeatedly. And I think those of you who've been schooled in Newtonian mechanics will kind of hopefully come to appreciate the fact that it's a nice thing that you can tack on to Newtonian mechanics without going full-blown relativity. It's just a different way of thinking about inertial frames. All right.
So here's the where maybe for you, you don't necessarily need to take this into any account, but this is where things get weird for me. When things start rotating in 3D, and you have to account for Coriolis, and you have to account for acceleration in various directions, and you have to account for what else? The angular momentum stuff, centrifugation. I have dark memories writing 3 lines of equations just to start. And so, yeah, things get complicated very quickly when things start doing that. Are
you talking about something as complicated as Euler's equation for rigid body rotation? Does that sound familiar at all? I mean, I don't think you would have maybe gotten that far along.
No,
Okay.
even earlier. Maybe it's somewhere equivalent, but we used to do it only with vectors. So, you have ijk, and then all you had to do was count all the forces on every vector, which sounds easy enough, but then it's a nightmare.
So you're talking about torques in 3 dimensions where you're doing cross products and all of that. We're not going to do that. We're not going to do that. Cool. Yeah. No, I'm not. I don't want to. I don't think there's anything to be gained really from doing. Although it is. I have a certain love for full 3-dimensional statics problems where you have 3 torque equations, 3 force equations. You end up with 6 equations and 6 unknowns, and try to solve them. It's beautiful in its own right, but there's no real insight that's gained from that you can't gain from just talking about simple rotations in a 2-dimensional kind of a space, right? Rotations around axes that are perpendicular to the 2 dimensions in which everything else is happening.
Yeah, you'd think so, but once you get into these things, the math becomes very messy.
The math gets messy, and there's no particular insight.
This is where you get 0 equals 0.
Yeah. So I won't go into that, although rigid body rotation is really interesting. I have a story about that. My friend Pinky, who was an astronaut who flew on 3 space shuttle missions, including the ones before and after the Challenger disaster, was also, I think, one of only 2 people ever to do a tetherless walk in space. And I think maybe the only one to do one for a purpose. He went out from the shuttle to retrieve a satellite that had lost communication. The Earth had lost communication with because it had tumbled out of orientation. We couldn't. The antenna wasn't pointing at the Earth in any constant fashion. So what he went to do was to try to go out and hook himself up to it. He had a special harness. He was going to hook himself up to it and then jetpack it back to the shuttle bay where they were going to work on it and then send it back out again. And it turned out that the harness that they built failed to hook up. So he went out there, linked up with the satellite, or tried to link up with the satellite, moved in very slowly, tried to attach to this nub on the satellite. They had designed this $1 million harness that was going to do this linking up. But what they didn't realize that just before the launch of this satellite, somebody had put an insulating blanket over the nub that he was trying to attach to. So the harness didn't work. He did end up going up, trying to kind of grab the satellite, but ended up putting it into a spin, ended up giving it some angular momentum. And then there was it was the classic physics experiment of an object, a rigid body rotating with constant angular momentum about axes that were flailing about randomly. So it's hard to imagine until you actually see such a thing, in person. And Pinky talked about standing in the shuttle while they were figuring out what to do next, watching this satellite tumble, trying to predict what its next rotation was going to look like, and just couldn't do it because of the fantastically complicated mathematics of constant angular momentum rotation around a body that has 3 different principal moments of inertia, like this satellite did. Enough said. I mean, it's hard to explain exactly why that's so complicated. But it's like taking a tennis racket, throwing it randomly in the air. It's going to rotate in a very peculiar fashion that you will have a hard time predicting, except it's short-lived. It's influenced by air resistance and
Is
bunch
it
of
not
other
like
things.
rotating the phone? Like if you throw your phone up, it just goes all crazy?
Well, so it's related to the fact that the phone or a tennis racket is maybe a better example. You can take a tennis racket by the handle and flip it up, have it go through a full spin, and grab it by the handle again if you spin it in such a way that the head is, what do I want to say? The head is in the plane of the rotation. But if the head is perpendicular to the plane of rotation, like as if it were sweeping up air, right, as it rotates. Oh, this is so hard to describe. There's always,
I get it.
yeah, there's one axis around which you can't stably make something rotate. Any rotation around that axis is unstable, and it ends up going into these weird motions. And the phone is like that. You can flip the phone, around an axis through the face of the phone. You can spin it around an axis along through the long dimension of the phone, but you can't spin it stably around an axis through the short dimension. If you take an axis side to side of your phone, throw it in the air, you won't be able to make it spin stably around that axis. I recommend if you try this, do it over a couch or something, because you probably also won't be able to catch it. But it's related to that fact. Yeah.
Isn't this called the intermediate axis
That's right. Intermediate
problem
axis
or
theorem. Yeah.
or problem?
Yep.
I'm not sure.
Yeah, that's right.
Yeah, that was one of the fights, now I remember, between the electric current and what else? The relativity twin paradox.
Say again.
I
I'm not,
graduated from stacking blocks to flipping the TV remote.
I was
That
going to
the
say,
thing that got me past blocks.
I had, I've told this story, probably some of you have heard it before, but I had a student years and years and years ago who had been in the class where I had talked about intermediate axis theorem. We talked about rigid body rotation, and I'd mentioned that fact that the rotation around the intermediate axis is unstable. And Richard Feynman came to town, as he did every year or two, for a question and answer. He's just down the road, so it wasn't a long trip for him. He would come to town and he would have a session where he would he wouldn't give a talk. he would just take questions. He would only take questions from students, and he would only answer the question if the student could convince him that they knew enough about what they were. They weren't just asking some, "Wow, how do you do this thing?" It needed to be something that the student really understood something about, and then he would answer it. So he had to make all those decisions. And so my student asked him, got on stage and asked him if there was a simple way to understand the intermediate axis theorem. There was a simple way to understand why the rotation of an object around its intermediate rotational inertia axis was unstable. And Feynman, I think just the question convinced Feynman that he knew what he was talking about. So Feynman went in to put his hand to his chin and thought for 5 or 10 seconds, maybe 30 seconds, and then said, no. His answer was just no. There is no easy way to understand it. And my student was completely beside himself with joy. He had asked Feynman such a good question that Feynman couldn't give a simple answer to the question.
So apparently John Elliott in the chat could flip the racket in the way you described and still catch it neatly.
Let's see, what does he say here? I hold the racket with the level with the ground, facing the ground, the sky, then toss the head of the racket upward. It always neatly does a full revolution and a spin. Yeah, that's right. That's what typically will happen is you'll see it go up and it'll kind of execute a very quick like half spin or something, and then you can catch it. It's really hard to make it go through a full rotation without doing that spin around the handle. I think that's what he's saying. Yeah. Yeah, and that's a good one. Tennis racket's a good thing because if it falls on the ground, you won't break it probably. So do it with the tennis racket if you still have one. Well, okay. Any other things? We'll wind down here, I think. I'm going to, on the way out today, I'm going to play another song by my favorite friends here in town, Rex Holmes. They're a great band. I get to play with them occasionally, individually, never with the band, but these are guys that are my homies, and I think they're a great band. They do incredible power pop. So we'll play you out with, I think I played She Takes the Bus on the way in this morning. I'm going to play Always Looking on the way out, and we'll